Welcome all. I'm here to explain about the spectral and the magnetic characteristics of the transition metal complexes. Let's see what is the transition element. Transition element is also known as a transition metal, which has a partially filled d orbital or an element that has an ability to form stable cations with an incompletely filled d orbital. In general, any element which corresponds to the d block of the modern periodic table, it consists of group 3 to 12, which is considered as a transition element, and mostly the F block element, that is the lanthanide and actinoids, is considered as a transition metal, in which it is known as the inner transition element. Let's see the properties of a transition element. These elements form colored compounds, and this color is explained by the dd transition of electron. And there is a relatively low gap in energy between the possible oxidation state of these elements, and the transition element therefore exhibits many oxidation state. Many paramagnetic compounds are formed by these elements because of the unpaired electron in the d orbital. And transition metal have large ratio of charge to the radius. Transition metal tends to be hard and they have relatively high densities when compared to other elements. The boiling point and the melting point of these elements are high, so that it participate due to the participation of the delocalized d electron in the metallic bonding. And this metallic bonding of delocalized d electron also causes the transition element to be a good conductor of electricity. Let's see the origin of magnetic properties. Spinning of charged particle generates magnetic field, and the electron and protons are the charged particle which is spinning on its own axis, so having the magnetic field around it which generates a magnetic moment. Let's watch the motion of an electron. For an atom, contribution of the magnetic behavior is mainly due to an electron. That is, an electron can create a magnetic moment in two different ways. That is, electron spinning on its own axis and the electron revolving around the nucleus in a closed path, which is spinning in its own axis is known as the spin magnetic moment, and which occurs due to revolving around the nucleus in the revolving around the nucleus in a closed path, that is due to the orbital motion, which is orbital magnetic momentum. And here the unpaired electron have magnetic field in its own vicinity, whereas the paired gets cancelled out each other. What is a diamagnetic substance? Compounds having all electrons in the paired form, as a result of which the net magnetic moment value is 0, is known as a diamagnetic substance, and these substances are repelled by the external magnetic field. Paramagnetic behavior. Paramagnetic substances are those which have unpaired electrons having some resultant value of the magnetic moment, and these substances are attracted by the external magnetic field. So higher the number of unpaired electron, the greater would be the paramagnetic character. And let's see the magnetic moment. The total magnetic moment can be written as spin magnetic moment, that is mu s, plus orbital magnetic moment, that is mu l, which is written in terms of Bohr magneton. That is, one Bohr magneton is equal to E h bar by mc, which is E h by 4 pi mc, that is 9.274 into 10 raised to minus 21 erg per gauss. Here this is only for one electron, so we have to see for the metal in a complex. So we look for the number of unpaired electrons, so we go for the other calculation, that is mu s, which is the magnetic moment, is equal to g root of s into s plus 1. Here it is an example for hydrogen, in which half is being spin is given as half, that is 2 root of half into half 1 by 2 plus 1, which gives root 3, In terms of Bohr magneton, it is given as 1.73 Bohr magneton. And here G is a gyromagnetic ratio, which is also known as a G factor. That is the Landé G factor, which is 2.0023 for a free ion. And let's see the magnetic moment of a 3D transition series, that is mu S plus L is equal to root of 4s s plus 1 plus L into L plus 1, where we know that S is the total spin moment and L is an orbital angular momentum. And in case of D block, the 3D series, due to the orbital motion of electron, it generates a magnetic moment and it interacts with the environment electron, and the equation is mu s plus 1, that is equal to 4s plus 1 root of 4s into s plus 1 plus L into L plus 1. Here due to the orbital motion, there is a magnetic moment is being generated here. And here we can see the first transition series, that is from D0 to D10 is being written here. And in the beginning of the series, the value range is somewhat the similar, that is mu s, which is represented in Bohr magneton, would be similar to the observed value, that is till D6. But later half series, the value from 4.9, that is D6 onwards, the value gets changed, that is it gets increased. So the thing is that we have assumed orbital angular momentum as a 0, but it is not 0, it is partially contributing to the system, that is L is being partially quenched. It is not being quenched, it is partially contributing to the system. So why it is partially quenched? We are taking D block series and moving, we are considering the D block series, and from moving from left to right, we notice that size is being decreasing. So the interaction decreases, so it contributes. So in later half series, the observed value increases comparing to the mu s calculated value. And for 3D series, the equation is mu s is equal to root of 4s into s plus 1, where L is equal to 0, that is quenched due to the external interaction, that is environmental interaction. And for 4D 5D series, mu s is equal to root of 4s into s plus 1 plus L into L plus 1, where L and S is being contributing, so and they are not coupled. And in case of lanthanoids and actinoids, mu is equal to G into root of J into J plus 1, where G is the Landé splitting factor, where G can be written as 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 whole divided by 2J into J plus 1. But if we are considering for a free ion, the L would be 0 and J will be equal to S, so that we can write it as G is equal to 1 plus S into S plus 1 plus J into J plus 1 divided by 2J into J plus 1, where these J terms are being replaced by S, that is G is equal to 2. Now let's see the spectral properties of a transition metal complex. A substance exhibits color because it has the property of absorbing certain radiation from the visible range and radiates the complementary color of the absorbed light. So in transition metal complexes, the energy difference between two sets of d orbital is very small. Thus an electronic transition between low energy d orbital can be easily achieved by absorbing low energy radiation and reflect them also in the visible range of spectrum. And the DD transition depends on four factors, that is oxidation state of the metal, number of ligands present, nature of ligand, geometry of the complex. With the visible spectra, it is possible to predict the color of the complex, and from the plot we can find, from the plot of absorbance versus frequency, the absorbent maxima is at the wavelength, that is 5000 angstrom is equal to wave number, that is 20300 centimeter per. Energy associated with wave number is given as 240 kilojoule per mole, and since the difference in energy levels between T2G to EG varies with the nature of metal ion, the ligand and the geometric complexes absorbs the radiation from different region of the visible band, and hence it gives different colors. So far we have come across what is a transition metal, what are its properties and its magnetic properties and the spectral properties. Thank you.